Hey everybody, just a mic check. If you can hear me, say so in the chat. Thanks. Hey everybody, welcome to episode number 14 of Goldendale Observations, coming to you live from the new Goldendale Observatory. I'm Troy Carpenter, and tonight we'll be talking about the planet Mercury. I brought up the planet Mercury a few times during our shows in the past, but in this particular case we'll be talking about how best you might view the planet Mercury. As the title of the show suggests, it is the most elusive of planets, which might surprise some of you. Some of you may have already seen Mercury over the last few days. The timing is very important, and we'll talk about why that is during the show. This may be, and I should never make these promises because I'm always wrong, but this may be the shortest show we do because the science here, if you want to call it that, is not terribly intense. There's not a lot of material to go over when it comes to this topic. But that being said, because we will have extra time, feel free to ask questions. In fact, I insist that you do. Not just questions, but also make comments. And don't be afraid to ask questions about things that are only vaguely related. We do like tangents. And you'd be surprised how many tangential topics can be pulled back towards the subject matter at hand. Those of you who have never heard this spiel before, Goldendale Observatory is a public facility. We are an educational observatory, so please ask questions. We want you to learn stuff and also hopefully be a little bit entertained. That's nice too, because science is fun, right? I can tell you from experience, I have met professors and I have met scientists who are actually very enthusiastic about their work, and yet they cannot convey that enthusiasm. And so people get the impression that science is boring, that topics like these are arcane, that only a very small number of people might find them interesting. Part of the reason people assume that is because they incorrectly believe they cannot understand this stuff. And as I mentioned in previous videos, in this age of wonders we inhabit, it is now possible for regular folks who are not, for example, career astronomers, to learn quite a bit about astronomy. Very deep stuff indeed can be known by anybody who has, for example, a connection to the internet. And it's not just via videos like this, it's also via, independent research. You can sit down with your smartphone and learn about all sorts of things simply by Googling stuff. That being said, not everything on the internet is true, so it's good to stick to reputable sources on mainstream topics. And by the way, that's why it's also important to ask questions of people who do know more about the stuff. So clearing up any misconceptions there might be. So, on that subject, I absolutely love the stars and the celestial bodies, someone says. Well, that's nice. It's never been a better time to learn about them, and I don't just say that, I mean it. Hi, everybody. Good evening. Oh, yeah, someone says, I can't wait to come up to the observatory. I appreciate that sentiment. We do want visitors again, and one day we will be open again, and hopefully this facility will be packed with human beings. Okay, so we're going to talk about the planet Mercury, like I mentioned. Mercury is actually not a terribly interesting planet as planets go, and that is because it is not known for its surface features. It is very moon-like in its appearance. If you don't believe me, let me show you. Almost invariably, when I put this picture of the planet Mercury on the screen here at the observatory, someone will conclude that it is Earth's moon. And no, it's not. That is the planet Mercury. So in the interest of filling time a little bit, let's share some trivia. Who can tell me, why is it that Mercury looks like Earth's moon? Someone tell me. I'm going to wait for the answer and drink from this giant jug of water while I wait. Why does the planet Mercury look so much like Earth's moon? What do you think? I'm watching the chat. No, nobody? Nobody's going to respond to that simple grade school science question? What do you guys think? No atmosphere? Good. So lack of atmosphere means that the planet's surface gets clobbered. And not only does it lack atmosphere, it also lacks erosive properties like rain, wind, plate tectonics, continental drift, which on Earth will erase craters. As a result, not only does Mercury get clobbered, it retains a record of most of those impacts. And so that's why it looks the way it does. Interestingly, due to ultraviolet radiation from the sun, because of course Mercury is very close to the sun, the material on the surface of the planet Mercury is darker. It is a lower albedo than, for example, moon rock does. And so Earth's moon actually appears more white by comparison. I don't know if this picture will show that, but it does. So you can kind of see the grayness of the Earth's moon, less of that brown color you see on Mercury. And that does have some pertinence when it comes to the show we're talking about tonight. So yeah, planet Mercury, because of its lack of surface features, because of its lack of interesting atmosphere, because of its lack of clouds and whatnot, and also because of its size, it tends to be a rather unremarkable planet to view through a telescope. And when I say size, in case you forgot, Mercury is quite tiny. There is an image of Mercury there compared to Venus, Earth, and Mars, and these are all drawn to scale. As you can see, the planet Venus is only slightly smaller than Earth. Mercury is much smaller. And even Mars is bigger than Mercury. Now, I'm going to share with you some interesting trivia. I want to ask a question. As a wait, hold that thought. I'm going to read the chat really quick. Good. Someone mentions that it has phases. We're going to talk about that. Actually, let's do it right now. I would say the only thing Mercury has to offer when it comes to viewing it through a telescope is phase. Now, I'm going to show you a picture we took of the planet Mercury through our big telescope here at the observatory back in 2013. Now, as you can see, it appears as a speck, but let's zoom in here a bit. Oh, look at that. I only see half of Mercury. And that's because, just like Venus, more famously, Mercury also exhibits phase angle from our vantage point. As we've discussed multiple times in multiple videos, phasing is not real. It is a figment of our perspective. Because of where we are, because of where Mercury is, we do indeed see it manifesting phases. It is, however, less famous for this than Venus, because Mercury appears smaller, for two reasons: because it actually is smaller, and also because it's farther from us. We'll get to that. So in a normal telescope, it might be hard to actually perceive this phase. On Venus, it's much easier. On that subject, watch this. Here is a deliberately incompetent, inept photograph. This is from May of 2020, so last year, May of 2020. We had a beautiful conjunction of Venus and Mercury. Now, I took this is funny, on purpose, just for fun. This is an example of eyepiece projection. So I had a 6-inch Newtonian reflecting telescope, and I had it pointed at the conjunction. And then I put my cell phone up to the eyepiece. This is, again, the worst possible way to take pictures. Unfortunately, it is also a very common way to take pictures. But I was proving a point that you can take surprisingly decent astrophotos using an incredibly flawed method if you're very steady with your phone and you know how to set the focus on the telescope. The reason I wanted to show you this image is because you can clearly see that Venus has a phase, even at this low magnification, where Mercury simply looks like a dot. So we have a speck versus an obviously phased planet. So Venus appearing so much larger, the phase angle is more noticeable. But both of these bodies do have phases when viewed from Earth. They are the only two planets that exhibit strong phasing. And you guys probably know why. It's because they are closer to the sun than us, right? Here's an example of the sky right now, or actually not, this is the future now. What year is it? 2089. I've had this running for a while. And as you can clearly see, Mercury and Venus are inside of Earth's orbit, so to speak. Mars and beyond are out. And we refer to them then somewhat derogatorily as the inferior planets. Mercury and Venus, the inferior planets, will always experience a very starkly alternating phase angle because we can watch them go around the sun. And so we can watch them being illuminated from one side or the other. Speaking of that, let me go back to that picture of Mercury. Somebody tell me, where is the sun in this image? Somebody tell me, where is the sun in this picture of Mercury? What do you think? Let's make it easy. Is the sun on the left or the right? What do you think? I'm watching the chat. Lower right. Very good. Exactly right. You got it. It was very specific. You can tell that the sun is to the lower right because that's the side of Mercury that is illuminated. So now this is a deliberately ridiculous question. What is casting the shadow that blocks the rest of the planet? It's kind of a joke question, but let me see if you can tell me. What is creating the shadow that makes the rest of the planet invisible? What do you think? I'm watching the chat. Nothing? What's casting the shadow? Mercury itself. Very good. So, no, not Earth. Who said that? Oh, my goodness gracious. So, I bring this up because more commonly people assume that moon phases are the result of Earth's shadow. That would be an eclipse. You're not seeing an eclipse. When an object has phases, you're seeing the shadow of the object itself. So Mercury itself is getting in the way of the sunlight. And by the way, that's what we call day and night. So right now it's nighttime here, so you're standing in the shadow of Earth. Make sense? Yeah. Now, one thing I would like to go over in the show a bit tonight is terminology. We're going to talk about the difference between east and west and celestial east and west. So let's go to the sky simulation that I use so often during these shows. This will be our first term for the night. We're going to learn about celestial east and celestial west. So this is the sky right now. Let me zoom back a few hours. Okay, it's daytime. Let's make it noon. I'm going to turn off the sunlight. Turn off the meridian, turn on the meridian rather. The meridian is that vertical line you see that divides the sky into east and west, or rising and setting. So the rising would be over here, setting would be over here. Now, we're facing south in this simulation. And I see the sun. I also see the planet Venus here. I see Jupiter. I see Mercury. By the way, if I get really close, you'll also see Saturn. You guys might recall, not that long ago, we had the great conjunction of Jupiter and Saturn. And you won't be able to see that right now because the two of them are so close to the sun, they will of course, be lost in its glare, as you can see. Now, in your opinion, is Mercury to the east or west of the sun? There's Mercury there. There's the sun. In your opinion, is Mercury to the east or west of the sun? What do you think? We refer to this as celestial east. And so everything over here is celestial west. So something on the west side would be, okay, good, you got it right. No, not west. So anything on the right side, so to speak, in this image would be celestial west. And anything to the east, or the left rather, would be celestial east. Now that's actually common sense if you're facing south because, of course, east is over there and west is over here. But this does confuse people a bit. So that's why I wanted to show it to you. Now, specifically, the reason we're talking about Mercury tonight is because right now, Mercury has achieved what is known as greatest eastern elongation, not to be confused with greatest western elongation. So watch this. Let's go into the future a few hours. I'm going to turn the atmosphere back on. By the way, the ground is there. I'm going to turn the ground off, but you know where it is. So sun's going to set. Here comes the sunset. There you go. Oh, look, and there's Mercury. As you can see, the sun is well set, and yet Mercury is apparent. You guys might be surprised to learn that Mercury is the most difficult planet to observe. And the reason is simple. It hangs out close to the sun. From our vantage point, Mercury appears close to the sun, and as a result, it tends to be lost in the glare of the sun, and you cannot observe it. So the best time to observe Mercury is when it is at what we call greatest elongation. In this case, eastern elongation, which allows you to see it in the evening after sunset. If it was on the other side, not surprisingly, we would refer to that as greatest western elongation, And you'd see it when? When would you see Mercury during greatest western elongation? Let's see if you understand this. What do you think? When would you see Mercury during greatest western elongation? What time of the day? What do you think? I'm watching the chat. Morning, that's right. So in the early morning, you'll see Mercury easiest if it's at greatest western. And again, in the early evening, you'll see it when it's at greatest eastern elongation. I have more to say about that, but are there any questions so far? Let's go back to that simulation of the sky. Let's pause time. Let's find a good spot here. Let's pause. Okay, there's the Earth. Now you tell me, based on the simulation you're seeing in front of you, would this be a good time to see Mercury? What do you think? Right. Oh, see, someone said Eastern happens on the west while Western in the east. That's exactly why I wanted to go over those terms, because people constantly flip these, because common sense would indicate that the east would be in the east and west would be in the west, but that's the opposite of true, because it has to do with where they are in relation to the sun. Now, I asked if this is a good time to see Mercury, and you guys are all saying no. Good. You're saying, well, sun is blocking. That may not be quite true. See, the sun is not actually completely in the way, but it is going to be so close to Mercury that Mercury will be out in broad daylight, and of course, you'll lose it in the glare. Good job. So let's go into the future. Okay, now let's see. Now look, Mercury has zipped all the way around. It's now on our side of the sun and a little bit farther to the right. Now, this is where we're going to test you a little bit. Do you think that Mercury is to the celestial east or west of the sun? In this particular simulation, what you're seeing right now, is Mercury to the east or west of the sun? What do you think? Sliver. What do you guys think? Is it to the east or west of the sun? Oh. Right. So it's in celestial west. Very good. So Mercury appears to the west of the sun from our vantage point. Good job. Questions about that? Let's go back in time a few. Oops. Let's go back in time a few days. Now we're going backwards in time. As you can see now, Mercury appears to the sun's celestial east. So now the sun would set and then Mercury would set after it. So you'd see Mercury in the evening after sunset. But when we go back into the future again, let's go over there again. Pause it. Go over here. Now you'll see Mercury rise before the sun rises. And so it's going to be seen in early morning. So that means you would see it in the western sky in the evening. Correct. That's right. So in the case of where I had it before, right now I have it the opposite of that. So Mercury is to the celestial west of the sun. You'd see it rise before the sun in early morning. But the way I had it before, when the Mercury was on this side of the sun, well, that's when you'd see it in the early evening after sunset. Very good. Good job. Questions about that? You would think that Mercury would be easy to find or see because it is fairly close to us. In fact, I have a little trivia to share with you about that. How many of you know which planet is closest to Earth? This is one of those things we've been learning since we were little kids. Who could tell me? What planet is closest to Earth? I'm going to watch the chat. Which planet is closest to Earth? Yeah, Venus. Oh, no, Mars is not right. Venus is correct. It's true that we all learn in school that Venus is the closest planet because it's true. Venus is the closest if you were to measure it at closest approach. Venus comes within 25 million miles of Earth, which is by far the closest planet to Earth. Mercury, by comparison, comes within 48 million miles. However, you may have heard, this is funny. Are all the planets on the same plane? No, they're similar, but not exact. The planets roughly adhere to what we refer to as the ecliptic plane. They retain the inertia of their formation, and everything in our solar system formed mostly within a planar distribution of mass because of inertia flattening the enormous solar nebula as it collapsed. That's how star systems form. So everything in our solar system is roughly the same plane, but not exact, especially Mercury, by the way. This is a good tangent. If you look at Mercury's orbit, it's very clearly tilted if I turn on the correct simulation, watch this. Now look at this. Look how tilted Mercury's orbit is compared to the other planets. See that? Clearly crooked. All the planets are crooked, but Mercury is the least flat. Its orbit is the most crooked. It is the most, and by the way, the term for that is inclined. Mercury is the most inclined planet. Now, as I was saying, I'm going to speed up time again, let you watch all the motion here. We all learned in school that Venus is the closest planet because it technically, literally is. However, you may have heard last year some surprising news. It was one of those clickbait things where you see it like on Facebook or whatever. There was suddenly this suggestion that Mercury is the closest planet. It turns out it's true. On average, Mercury is closer to Earth because of its fast orbit. Mercury is going over 100,000 miles per hour. Its year is only 88 days long. So even though it's true that Venus technically gets the closest of all planets to Earth when it is closest, over time, Mercury is on average closer to Earth than Venus. I think that's fun. Again, that should imply that Mercury should be easy to see. It should be one of the easiest to find planets. And yet, Mercury is the most challenging planet to observe due to its proximity to the Sun and it being lost in the glare. Good. Now, I showed you a picture I took of Mercury with our big telescope. And you might notice the sky is blue. And the reason the sky is blue is because I took this picture in broad daylight. Because that's the best time to image Venus and Mercury. You guys might remember, we've talked about this a lot from previous shows. Earth's atmosphere is the enemy of astronomy. It does not make our lives easy because air distorts light. Air is not solid. It is an amorphous blobbing mass that changes shape constantly. And I always show this video of Sirius twinkling. This is the bright star Sirius. And this is what happens. Light from space objects is heavily distorted by the atmosphere always moving and changing. You may have heard that planets don't twinkle. There is some truth to that, but it has to do with surface area. Because they are larger, they present a larger surface area. Or, excuse me, not larger. Because they're closer. Because planets are so much closer than stars, they present a larger surface area, and so their light is better able to overcome atmospheric scintillation, but they're not able to do it completely. And so planets do get distorted. And by the way, even though it's true that, for example, I don't see Jupiter and Saturn scintillating or twinkling very much, Mercury, absolutely. If you wait to see Mercury at the end of the night when it's really low, you will see that it twinkles just like a star, and that's Earth's atmosphere. So, believe it or not, the best time to observe a planet is broad daylight because now you're pointing your telescope up, and you're looking, or in the case of Mercury and Venus anyway, they're going to be closer to the Sun. You're going to be pointing your telescope higher in the sky. There's less atmosphere in the way. So, in the case of this picture of Mercury that we took, I would not be able to get a picture like this right now because Mercury being low, its image would be horribly distorted. That's one of the reasons why it's good to observe planets like Mercury at elongation, where you care about how far it is from the Sun, for convenience sake with the naked eye. But when it comes to imaging it or studying it for science or, I don't know, amateur astronomy, you want to do it in broad daylight. That's the best time because you're looking through less air. Any questions about that? Oh, someone asked, any idea why planets orbit quicker or slower? Because they have to, of course. So, let's go back to that. So, as you can clearly see, Earth is slower than Venus. Venus is slower than Mercury because of their relative locations to the Sun. The Sun's enormous gravity means that the closer you are to it, of course, the more, let's say, in jeopardy you are falling into it. This is basic orbital science. A body will have to go faster in order to experience enough centrifugal force, which is, by the way, actually just inertia, to beat the Sun's gravity. So yeah, Mercury is going well over 100,000 miles per hour, while Earth is going only 66,000 miles per hour. Yeah, that's very important. By the way, objects that get even closer to the Sun, like comets, for example, comets can be going over 1 million miles per hour when they get close to the Sun. Let me show you that. I'm going to turn on the comets here really quick. Watch this. See Comet Encke? Zoom. See that? Let's see another comet coming here. Any even closer than that? Looks like Comet Encke will be the best example in this simulation. As you can see, it's practically crawling along here, the comet barely moving. But as it inches closer to the Sun, watch what happens to the velocity of this comet. Watch. And whoosh. See that? Comets often have highly eccentric orbits, which means they're highly off-center. And the more eccentric an object's orbit is, the larger its increase or decrease in speed due to proximity to the body it orbits. Mercury experiences over a 30% change in velocity when it's orbiting the sun. That's quite a significant change, and that's because Mercury's orbit is the most eccentric of all the planets. So if you look, you can actually tell that Mercury's orbit is eccentric. You can see that the sun is closer to this lobe here than this one. By the way, those of you who might recall learning that Pluto was the most eccentric and inclined planet. Sure, that's true. When Pluto was considered a planet, he had the distinction of being the most eccentric and the most inclined. Eccentricity, again, is how off-center you are. Inclination is how crooked you are. Now that he's out of the planet club, Mercury gets to be, once again, the most crooked planet, the most inclined and eccentric planet. Let me change that vantage point there. You can clearly see how tilted its orbit is, so to speak. But comets and asteroids are known for having much more crooked orbits because they are minor bodies. They're much more easily perturbed by major bodies. Small bodies get thrown all over the place, and they tend to have wild and crazy orbits as a result. So is it true of Venus? Yes. So Venus, too, clearer in daylight. If you're looking when it's straight up, so to speak, you're going to be looking through less air. That's right. There's a little bit of strategy to that. These are good questions. Let's go over some terminology. Yes, Mercury does rotate, and of course, all planets rotate. They have different day lengths. I might have a little bit of trivia for you on that topic. Let me see really quick. If I don't have it handy, oh yeah, let's see. I thought I had the day on there. I guess I don't. Sorry about that. Don't have it handy. Let me go back to my chart here of all these motions. I want to show you guys an image that depicts different positions, and I want to make it clear what we're talking about when we discuss for example, elongation. So, all right, this chart, it looks like some kind of astrology thing, but it's actually an astronomical chart, I promise. This is not nonsense. This particular chart displays the planetary orbits of Mercury, Venus, and Earth. The orbits are rendered as perfect circles, so just be aware that's not the case. That's because the purpose of this chart is not to demonstrate the exact nature of their orbits. We're talking about positions. Okay, so if this is the Earth here, then these different positions represent our different vantage points. Just to get these out of the way, because they're not part of the subject, these positions here, this one and this one, are known as Western and Eastern quadrature. These have nothing to do with the conversation at hand. I just wanted to point them out if you were curious. The ones I want to talk about are these and these. Let's go over this one first. This position here between Sun and Earth is, of course, known as conjunction or inferior conjunction. This is actually known as conjunction if they're beyond the sun. Unfortunately, that word gets used a lot in astronomy. You've heard me use the word a lot. For example, we just did it recently with the whole Jupiter-Saturn thing. In the case of inferior conjunction, that implies that the body is between us and the sun. And you might be aware that a very exciting thing can sometimes occur during inferior conjunction. Let's see if you can tell me. What exciting thing occurs sometimes during inferior conjunction of a body? Can anyone remind me? I bet you can tell me. What exciting thing can sometimes happen during inferior conjunction of Mercury and or Venus? Transit, very good. So, this is 2016 transit of Mercury, and as you can see, this was shot here at Goldendale Observatory. That little black dot is not a sunspot. That is the planet Mercury transiting the sun. These don't happen very often. The last one was in 2019. They tend to happen in pairs like that. Transits are exciting events. Mercury transits happen enough that you can expect to see a few in your lifetime, but Venus transits are much more rare. We had a Venus transit back in 2012. And let me make that smaller. Get my head out of the way. Actually, I'll move my head. There we go. And watch this. This is the transit of Venus. Notice how much bigger Venus looks for two reasons. Remember what I said, that even though technically Mercury is the closest by average, Venus is closest overall when she is actually between us and the sun. Venus appears bigger because of that, because of proximity, but also because of actual size. Venus is about the same size as Earth, only a little bit bigger than Mercury. And so, yeah, Venus transits are much more rare. The next one won't happen for, let's see, 105 years, is it? Yeah, 2017. Oh, so time flies, wow. So less than 100 years, but still quite a long time in the future. Venus transits and Mercury transits, rare events that occur only during inferior conjunction. Remember that term. So again, when the planet is here. Now, as you saw from that three-dimensional animation of Mercury and Venus zipping around the sun, inferior conjunction happens a lot. So you might think, oh, well, then why don't we have transits a lot? Because, like we discussed earlier, the planes of the orbits, they're not perfectly aligned. All of the planets have their own eccentricity, which is how offset they are, and inclination, which is how crooked they are. Because the planetary orbits are inclined eccentric ellipses, the odds of an exact alignment are quite low. Now, someone asks, why is it? Yeah, June 2012, May. Oh, yeah, that's right. So, Jim White, your birthday, that was cool. What a birthday present to have, an actual Venus transit on your birthday. That was great. That was a great day. Since you're bringing it up, I will tell a Venus transit story. I chased an opening in the sky. The clouds were awful that day, and I was on the East Coast. And I drove and drove and drove, trying to get out from under these clouds. And I hit Cape May, New Jersey. I was on the edge of America. The Atlantic Ocean was there. And yes, it was clear enough for me to get those pictures. But I almost missed it. If the clouds had been just a little bit closer, I would not have been able to see that transit. Yeah, transits are worth driving for if you've never seen one. They're rare events. Now, as I was saying, the reason you don't have transits every few months rather is because, again, the orbits are crooked. By the way, this is the same reason we don't have lunar and solar eclipses all the time. You would think that every time we had a full moon, for example, we should have a lunar eclipse, and then every time we have a new moon, we should have a solar eclipse. That would be true if the moon's orbit agreed with the plane of our orbit. Of course, it doesn't. So these alignments are rare. Questions about that? All right, let's see here. So that's a great question. Someone asked, what phase will Mercury be during those greatest elongations? So that's a great time to talk about it because we have this chart right in front of us. So you can actually see, in this case, elongations marked here and here. And as you can see, from our vantage point, the phase angle will be essentially a quarter. It won't be half. It'll be a little bit less than that. So you'll see that there's actually a crescent-like a shape to it. Let's prove that. Let's go to now. Oops. So here we are now. Let's go back to here. Mercury. Right now, Mercury is at greatest elongation to the east. As you can see, it's a little bit of half. I guess the term, I shouldn't have said crescent. I should have said gibbous. So there's a little bit more of a gibbous shape to it. If I go into the future a few days, it becomes more of a crescent. So it's the days directly after, in this case, elongation to the east. You'll see that it becomes smaller. Let's go into the future a bit more. Let's see, what's the next date? So the next elongation is March 6th. Not too far there. Okay, March 6th, and again, you can see it's a little bit more than half, so it's, in this case, a waxing gibbous, where before it was a waning gibbous. It depends on which side it's on of the sun. And again, of course, it's all determined by our line of sight, by our perspective. So on that chart, this here would be greatest eastern elongation, and this greatest western elongation. It's not as hard to remember as you might think when you consider where the objects would appear in the sky. So if you think of all this being on its side, these objects are rising in the sky. If you were looking in the west, let's do the east. If you were looking east in early morning, you would see Mercury rise first and then the sun. The opposite would be true when Mercury is at greatest eastern elongation. In the evening, the sun sets first, then Mercury follows. Questions about that? Why is it not transit of Venus that was used to prove relativity theory? Well, I assume you're talking about the gravitational lensing effect where the sun's gravity bent starlight. Starlight is going to be much more easily measured to bend because it's a much smaller, let's call it piece of light. It represents a much smaller surface area, so it's more obviously altered in position by the sun's light. Also, those rays of light coming from a star are going to be going in almost a perfectly straight line because the star is so far away. You wouldn't want to use a planet for that kind of experiment because it's close enough that you're actually going to have some variability in the trajectory of the rays coming off of it from our vantage point. So a star presents a very tiny point of light, and its light is going in a very straight line, so to speak, and it's going to be more easily measurable for relativity's sake in the case of trying to prove the sun's gravity bent starlight. Yeah, that's an interesting question. So I want to go over now how much more frequently these events occur comparatively. So if you want to see a transit of Mercury, you don't have to wait very long. Not transit, excuse me. If you want to see the elongation of Mercury, you don't have to wait very long. So let me show you. The one we're currently having is right now, January 24th. That's Eastern elongation. The next one is March 6th. That's Western. Then we have Eastern, May 17th. Western, July 4th. Eastern, September 14th. Western, October 25th. So you have 6 positions, 6 elongations, Eastern and Western, of Mercury in just the year of 2021. All those dates I just gave you were all 2021. Venus, on the other hand, March 20th and October 29th. On March 20th, Venus will be at greatest Western elongation, and on October 29th, Venus will be at greatest Eastern elongation. And of course, the reason that Mercury experiences more of these is because it's faster than Venus. Imagine that. Questions about that? Like I said, this was going to be a pretty short show. I don't have a lot to go over with this particular topic. I'm gonna look at my chat log a little bit more and encourage you to ask more questions. Hold that thought. By the way, someone asked how long Mercury's day was. It's 58, or excuse me, yeah, it's 58 day long day. It is still shorter than its year. So Mercury's year is only 88 days. So imagine that. Its year is only 30 days longer than its day. Mercury is not tidally locked to the sun, but it certainly is pretty slow as planet rotations go. And I should remind you from our exoplanet show, there are no tidally locked planets in our solar system. That is to say, a planet with a permanent day and a permanent night side. But Mercury would be a good candidate for that if you came back in a few billion years. It may have become synchronized, but that won't happen before the sun dies. So Mercury will never have a permanent day and a permanent night side. There are no planets in our solar system like that, although there are some moons like that, moon-planet arrangements. For example, Earth's moon is tidally locked to the Earth, so there's one side that always sees the Earth and one side that doesn't. 4 of Jupiter's moons are tidally locked. Actually, several of Jupiter's moons, more than just 4, are tidally locked to him. And then Pluto is doubly locked with Charon, so that's a doubly locked system. Yeah, so Mercury certainly has a slow day, but not slow enough that it's locked to its year, but close, 58 versus 88, yeah. So does a large sun coronal mass ejection reach Mercury in base? Sure, they reach Earth. So when a large coronal mass ejection occurs, material will strike a planet, and that's an excellent question. One of the reasons that Mercury is naked, has no atmosphere whatsoever, is not just his weak gravity, which means he can't really hold on to it. It's because Mercury is stripped of atmosphere by the sun. Being so close to the sun, constant solar wind plus violent events like the coronal mass ejections you just mentioned will strip Mercury of any gases that may want to accumulate on its surface. Literally, Mercury's atmosphere is millions of times, and sometimes billions of times, less dense than the atmosphere of Earth, for example. Depends on what gas you're measuring. And so it's a combination of things. Mercury being close to the sun, Mercury having a weak magnetic field, and Mercury having weak gravity, meaning that it will be stripped of atmosphere. That's a good question. Now, would environmental temperature be the biggest problem with walking on Mercury? No. The temperature extremes are similar to the same we would measure on the Earth's moon. Your biggest problem on Mercury would actually be the same as the moon, which is lack of pressure, obviously. You'd have no atmosphere to slow you down, so you need to land using retro rockets. You couldn't use parachutes. And then once you're on the surface, your suit has to provide 100% protection not just of temperature, not just of radiation, but again, in this case, of pressure difference, because it is essentially a hard vacuum. The surface of Mercury is essentially a hard vacuum, just like Earth's moon. I had a fun conversation with a grad student once about this. We were talking about how close some of our space probes orbiting Mercury have gotten to the surface. Famously, we smashed one of our spacecraft into Mercury, the Messenger spacecraft, and the orbit kept getting smaller and smaller and smaller. And people were pointing out that at one point, Messenger was going over 10,000 miles per hour, but only a few thousand feet off the ground. Think about that. That would be impossible on Earth, because if you're going that fast, of course, you would burst into flames because of friction. But it's possible for a spacecraft to be going over 10,000 miles per hour close to the surface because, again, there's no air. That would be a highly unstable orbit, by the way, because when you're close to a body like that, gravity anomalies will cause your orbit to decay quickly, because gravity is not uniform, because mass is not concentrated evenly and homogenized across the surface and also the interior. So the objects, the satellite's orbit would decay rapidly due to those perturbations from gravity anomalies. So yeah, you could not safely orbit a planet close like that for very long, even if it has no atmosphere to slow you down. That's a good question. All right, so I'm looking at my chat feed here. Is Mercury slowly drifting into the sun? No, it's actually moving slightly outward, actually because of the sun slowly losing mass. The sun has lost the equivalent mass of roughly the planet Saturn, which is about 100 Earth masses. So the sun has lost about 100 Earth masses since its birth, and because of that, believe it or not, planets are migrating very, very, very slowly away from it. Now, on that subject, since you bring it up, the story of Mercury's orbit is probably one of the most interesting things to point out about the planet. Some of you might know that it was the planet that foiled Newton, because as we got very good at astronomy in the 1800s, we started to realize that Mercury's orbit was broken. There was something wrong with Mercury's orbit. Let me show you what I mean. So Mercury's orbit precesses. Now, all orbits precess, which is when the entire orbit rotates. So imagine if I were to grab the entire orbit of Mercury and tweak it, that's what orbital precession is. But the problem was Mercury's orbit was not precessing at the correct speed. There had to be something else going on. And this led to the hypothetical planet Vulcan. Now, not the Star Trek thing. It was argued that there was a planet, an unseen planet called Vulcan, that was orbiting the sun and perturbing Mercury's orbit. And this was an attempted explanation for Mercury's physical precession. But of course, we never found Vulcan, which confounded astronomers. And the reason we never found it is because Vulcan does not exist. It wasn't until Albert Einstein came along with his relativity, and we realized that your passage through time is determined not just by you, but by your reference frame, especially as it relates to other bodies. So from Earth, from the vantage point of Earth, Mercury is time traveling at a different rate than we are due to its proximity to the sun and due to its great velocity. So Mercury is actually experiencing a different passage of time than we are due to those two metrics. So that was one of the more interesting things that we discovered about Mercury in the last century. And it was one of Einstein's eureka moments when he realized that his relativity solved the problem with Mercury's orbital precession. This was the planet that reminded us that Newtonian physics did not completely and absolutely and utterly explain the universe. There were still mysteries. And Newton didn't account for this relative passage of time. So that's an important Mercury story for you. All right, keep watching that. Let's go back to here. Let's go to Mercury again, just for fun. Going to speed up time. Watch its phase angle change, and of course it grows and shrinks due to its proximity with us. So this would be inferior conjunction when it's in between Sun and Earth. This would be conjunction, and by the way, that's a terrible time to view it. Even though it's full, so to speak, you would have trouble finding it because it would be close to the sun in the sky and overcome with glare. Yeah. All right, as I said, I'm going to look back at what is the physical composition of Mercury? Mostly like Earth, lots of silicate rocks, oxide, minerals, iron. It has an unusually large iron core by ratio to the rest of the planet, which still baffles us. We don't know why it is that Mercury's core takes up such a large percentage of its radius. It might indicate that Mercury was once a larger, more massive body that was annihilated and perhaps stripped of its surface material. We're not sure. By the way, Can you show on the program what Newton was seeing and why that didn't make sense? Well, not Newton wasn't seeing it, but because he died before we discovered this. But Newtonian physics predicted a certain precession of the orbit, and it didn't add up. It worked with everything else, but with Mercury we were noticing an error. So I don't have an animation handy to show you, so I'll just let me pause that really quick. Go back to now. So in a nutshell, actually here, let's do this. I have an idea. Go back to Mercury, turn on the orbits here. Now, we're going to use our imagination a little bit to help answer your question. You're going to notice that there's a sort of a wobbling hula hoop effect of Mercury's orbit. Notice how the orbit seems to be changing in angle. That's not really happening. The reason that appears to happen is because of the misalignment of our orbits, because Mercury's orbit is crooked compared to ours. But I want you to imagine, I'm going to pause. Actually, let's pause it. Imagine that if I had giant hands, I could grab onto the orbit and I could tweak it so that the entire orbit would slightly, let's say this node here would actually be here, and this node here would actually be here. That happens naturally, that precession of orbits, where the entire orbit itself rotates. We're not talking about the body within the orbit. We're talking about the orbit itself. That precession occurs at a known rate, and it's an extraordinarily slow rate. But we discovered that Mercury's precession did not agree with the predictions, according to Newtonian physics anyway. They perfectly agree with the predictions when we take into account relativity. I hope that explains it. I don't have a handy animation to help explain that precession of orbit much better than that. But okay, I'm going to read questions. So someone asked, oh, hey, that's a beautiful question. Someone asked how we named Mercury. It's one of the most logical planet names. You probably know that we name planets after deities. And in the case of Mercury, Mercury is the Roman equivalent of the messenger god Hermes, the Greek god. Hermes, the swift, the guy with the little wings on his head. He was fast, and it was absolutely appropriate that humans named Mercury after that deity, because Mercury is perceived as the fastest planet. And by the way, that lends itself to the reason why he's so difficult to observe. In the course of a year, you only have about 2 weeks to easily observe Mercury. Think about that. That's why I say it's the elusive planet Mercury, because even though it's out a lot, it's only easy to see about 2 weeks out of the year, because, again, it's proximity to the sun. The ancients noticed this. The ancients, look at the time difference. So Mercury will go from eastern elongation today, 24th January, to western elongation on March 6th. So that's not a very long time. It doesn't take Mercury very long to go around the sun from our vantage point. The ancients noticed this. They noticed that Mercury zipped around. By the way, I like to tell a story. I deliberately do not look up the position of Mercury and other planets so that I can be surprised. And this happened to me just a few nights ago. I was driving home from work, and I saw a bright thing in the west, and I'm like, what is that? That can't be a star. There shouldn't be a bright star there. And I knew it wasn't Jupiter, and of course it was Mercury. Yeah. So Mercury will sneak up on you like that. All of a sudden, one night it wasn't there, and then a few nights later, there it is. And it's remarkable to watch it change position from night to night. Watch this. Let's go back to that view of the sky. Let's go to the west. Let's see here. There we go. All right. Again, the green line. There's see the W for west. The green line is the horizon. Okay, now there's Mercury. See that? That's tonight. Let's go into tomorrow. Look at that. See how it went higher? And the next day, and the next day, and the next day. And then watch this, guys. It's going to start diving into the horizon. Look. And gone. At this time, it would be unobservable. So, zips around the sun very quickly. Again, his year is only 88 days long. Think about that. So, yeah, very, very poetically named planet, in my opinion. Hermes, the Greek. Mercury, the Roman, the messenger of the gods, the quick one, the fast one. Yeah. Now, someone asked a question, what was the first planet observed with a telescope? Well, the first planet discovered with a telescope is Uranus. We can't tell you when we discovered what we call the classical planets, like Mercury, Venus, Mars, Jupiter, and Saturn, because they've been known since before antiquity. People have noticed them for as long as there have been people, because they're bright enough to see with the naked eye. Uranus is only technically bright enough to see with the naked eye. No one noticed it with the naked eye and wrote it down. It wasn't until William Herschel in the late 1700s, early 1800s, he started studying bodies in the solar system, and he discovered things that weren't stars out there, in this case, Uranus. So Uranus was the first planet discovered with a telescope and not with these things. Yeah. Good question. Sure. Does Mercury have any moons? No. So Mercury and Venus do not have moons. And interestingly, part of the explanation for that might simply be their proximity to the sun. Being so close to the sun's gravity will perturb bodies. Perhaps an object could have been a moon of one of those two planets at some point, but it may have been perturbed away by not just solar perturbations, but other bodies as well. Our solar system used to be a much more violent and chaotic place during the period known as the heavy bombardment. Most of Mercury's craters were earned. Same with Earth's moon. It's possible during that time they may have had moons, maybe not, and if they did, they lost them via some mechanism. Yeah, so Mercury and Venus, no moons to speak of. Good question. This is fun. You know, we got a lot of these good ones here. Someone says, this is actually from the beginning. You encourage questions. I have something off subject. What is the winter hexagon and what is the significance? It's just a series of bright stars in the winter sky. I might do that. Let me hold that till the end of the show. That might be a good time filler. So, let's see. How did you know that was Mercury? Oh, well, I knew because of my job, I pay attention to the sky. And I knew that we had a greatest elongation coming up because we had already scheduled the show to correspond with it or coincide with it. But if you don't know, and by the way, that's a great question about everyday life, because you live in the future and we all have these things now, if you have a smartphone, you can get an app for your phone that will allow you to simulate the sky at any given time, including right now. And so if you look to the west and there's a weird thing there, you look on your phone and like, oh, that's Mercury. Yeah, so even if I didn't know that was Mercury, I could have found out using software like that. Notice I'm implying that you should use software and not a book or a planisphere. Planispheres, which are those paper tools that we use to predict the position of stars throughout the course of the year, are not useful for planets, of course, because planets move about on their own. They are not locked in place, so to speak, like the, quote, fixed stars. And by the way, there are no fixed stars. We only call them that because they appear so over short periods of time. But we know better, of course. The stars themselves also move. It's just that the effect is so subtle that in the course of a single human lifespan, you would never notice with the naked eye. With telescopes, we can measure that very precisely. But with the naked eye, you wouldn't notice that. You'd have to spend centuries of observation in order to notice the fixed stars moving. This is why we update star charts every 50 years. The star charts are not intended to reveal the position of planets because, of course, they're always moving. That's a good question. Thank you for explaining. Good. Of course, then all stars move. And the North Star is not always the North Star. And that's more because of Earth's axis wobbling, by the way. There's nothing special about the North Star. It's that Earth's north pole tends to point roughly towards it. We did a whole show about that. North celestial pole constantly moves in a 26,000-year cycle because of Earth's axis wobbling like a top. So we don't always have a North Star. There is no South Star. And the identity, so to speak, of the North Star changes because sometimes Earth's pointing that way, sometimes pointing that way. In about 14,000 years, we're going to have the star Vega, which is a very bright star, as the North Star. So there you go. That's convenient. Much brighter than the North Star, by the way. One of the most obnoxious myths that I deal with here at the observatory all the time is the misconception that the North Star is bright. It's not even the 50th brightest star. Its fame is not based on brightness, but on the fact that it's roughly consistent with the North Celestial Pole, and so you can navigate by it rather conveniently. Yeah. Yeah. Mercury being previously discussed as the closest planet to Earth on average, do we have any known or seen gravitational interactions on Earth because of Mercury? No, not something like tides, no. You can mathematically calculate it. Of course, all bodies affect all other bodies, including, by the way, this is going to sound ridiculous, including bodies that are billions of light years away. But the farther something is, of course, the weaker its interaction. And, of course, the weakness increases exponentially with distance. So, yeah, technically you could calculate some perturbation between Mercury and Earth, for example, but it's not something you would be able to measure empirically because the influence is just so slight. And the slightness of the influence is due not just to distance, but also Mercury's relatively small mass. If anyone's going to perturb anyone, it's going to be more Earth perturbing Mercury than the other way around, because Earth is significantly more massive. And by the way, when I say massive, I mean massive. I don't mean size. Size and mass are different things. See, so right here, someone asked a question, when approximately was Mercury first seen? I can't answer that because humans have known about the classical planets forever. As long as there have been humans looking up at the sky, we have noticed these bright bodies that move quickly through the sky. Planets were perceived as important because they were noticed to move independent of the stars, and that's why people thought they were living beings or even deities with great power. And again, I think it was very poetic or romantic, the naming of Mercury after the messenger god, because he's so quick, so speedy. Yeah. That was a boring thing to leave on the screen while I was talking. So, all right, questions. Questions. I'm looking at materials here. Like I said, this was going to be a short show. I'm pretty much ad-libbing right now. Let's see. How did the ancients see the planets? With the naked eye. Yep. Only. Didn't have, as far as we know, the ancients did not have optical aids. That's right. Okay, well. We're going to be wrapping it up on time, it sounds like. Let's do 4 more minutes of questions, and then I'm probably going to say goodbye for the evening. I'm going to leave this animation on the screen. Maybe it will inspire a few questions and comments. Yes, I agree. More people used to watch the sky before TV and smartphones, and also light pollution. Over 70% of all human beings live in cities or adjacent to cities, and so over 70% of all human beings don't really have access to stars. And I can guarantee that if you're just seeing a big blob of yellow light, you're probably not going to be looking at it very often. Yeah, so back in the day before lots of artificial light, I'm sure people also looked up a lot more, even without these distractions. That being said, I should also add something that I've learned. I'm not a history buff per se, but I know enough about history to know that people feared the dark. People feared the night, because the night was when the wolves would get you, or maybe the robbers. Maybe there's pirates, bandits on the trail. You don't want to be out at night because maybe someone's going to jump on you. And so people didn't like the dark, and we've always, as a result, associated light with safety. That's one of the reasons why cities are bright. People associate it with progress and civilization, and, oh, if it's bright here, no one's going to bother you kind of thing, and the wolves can't get you. Yeah, so I don't necessarily know that humans always spent all their time staring at the night, because at least for a significant portion of written history, they were scared of the dark. That's a fun topic. They actually did have some reason to be. It wasn't a completely unreasonable fear. Some of us grew up being afraid of the dark. I remember when I was a kid, I was afraid to go down the hallway at night because it was scary, because obviously darkness means ghosts or monsters or something. Obviously. This is all very scientific. Yeah, that's a good question. That was fun. Okay, so this is someone's already asked it again. This is a very important question. This is definitely worth addressing. So someone's asking again, why is it that the planets seem to stay in a plane? First of all, they don't exactly do so. As you can see, there is some variation. But then notice the orbits of the comets. Let's even make it worse. Let's turn on the dwarf planets. Let's go to the most famous one, Mr. Pluto. All right. Let me turn off the orbits of the comets here. Okay, Pluto's orbit is very much inclined, that is to say crooked, and eccentric in terms of being off-center from the sun. The reason the dwarf planets have highly inclined eccentric orbits is simple. Because they are minor bodies, because they have very little mass, they possess less inertia, and as a result, they will be easily perturbed off of the plane within which they were born. Minor bodies like dwarf planets, comets, and asteroids are easily perturbed because they simply cannot stand up to the great gravitational might of major bodies like planets. Now hold that thought, because I'll show you something. I use this picture a lot because it's fantastic. This is a real image. This is an actual image of a star system known as HL Tauri. This is a very young star system, a baby protoplanetary system where we have a protoplanetary disk with baby planets forming around a baby protostar. Notice we have an obvious planar distribution of material. and then we have the baby star in the middle forming. These grooves are being carved out by baby planets forming. The reason that a collapsing solar nebula takes on a planar distribution is simple. You have two forces battling each other. You have a centripetal, not centrifugal, a centripetal actor, in this case gravity, which wishes to pull everything in towards the baby star. And by the way, the star is the reason for the strong gravity. And then you have a centrifugal force, in this case inertia. By the way, there's no such thing as centrifugal force. It's a manifestation of inertia in this case. So it's a pseudo force. Inertia of these bodies wishes to carry them away from the star. So you have the battle between centripetal and centrifugal forces, and this naturally flattens the material into a disk. As a result, the majority of mass, the majority of material, remains either in the star or in the disk, and so the planets form there. They are inheriting not just material, but also great velocity. I mentioned earlier that Earth is going 66,000 miles per hour. It inherited that velocity from the material that it formed from within that disk. Understand that a planet going tens of thousands of miles per hour and comprising quadrillions of tons of material will not be easily deviated. I always like to use the example of a train. Try to divert a train that's speeding down the tracks at 60 miles an hour, and then try to divert a bicycle. Even a bicycle going 60, let's say that'd be very violent. It'd be very bad for the day. It'd be a very bad day for the bicycle rider. But you could divert a bicyclist going 60 miles per hour much more easily than you could a freight train. And that's not a bad analogy because the difference is about that extreme between, for example, an asteroid and a planet like Jupiter. So yeah, it's a very important question. The reason that planets tend to roughly adhere to a plane, in this case what we refer to as the ecliptic plane, is because they inherited that motion, they inherited that position, so to speak, during their formation, and they will not easily lose that speed. They will not easily shed that inertia. It takes another massive body to do it. And by the way, planets do collide, they do get flung away, they do fall into the sun, these violent things do happen. But for that to occur, some other major body has to be perturbing them. We now know that Jupiter and Saturn formed much closer to the sun. Let's pretend this is our baby solar system. As they migrated out, who knows what havoc they wreaked on the other planets. And it's almost certain that they caused all sorts of mayhem, including eating planets, throwing planets out, causing planets to collide, things like that. And I mentioned earlier, we know that the solar system used to be a much more violent place. We refer to that as the heavy bombardment period. And that's when all the rogue objects were still being shaken out, so to speak. The solar system we live in today is a lot more peaceful than it used to be because the unstable bodies have been dealt with, so to speak, either being flung away or falling into other planets or falling into the sun, etc. There's an entire family of comets known as the Kreutz sun grazers. And these comets, which number in the thousands, bombard the sun. Still to this day, objects are being eaten by the sun. All these billions of years later, yeah. So heavy bombardment hasn't so much ended as it has calmed down quite a bit. Good question. All right, so we're about to. Thank goodness they stopped migrating out, right? I guess. Sure, why not? You might know that there are some unaccounted for bodies in our own solar system. For example, you may have heard about hypothetical Planet 9. It might be lurking out there, but if it is, it's hard to find. Planets are difficult to detect if they're not close to a star because they don't give off much or any light. And so finding one that's far from the sun is actually quite challenging. So yeah, there could be a whole host of planets out there we don't know about orbiting the sun. Probably not too many, but there's certainly a lot more dwarf planets than we ever thought, including Mr. Pluto. By the way, that was one of the reasons he was demoted. Notice in this animation, or the simulation rather, all these red lines, all these red orbit lines, including that of Pluto, are other dwarf planets. And this is just a small handful of them. So there's plenty of them to be found. And again, notice how funny their orbits are compared to the more orderly orbits of the major bodies of our solar system. Yeah. All right, it's time to start wrapping it up. I was wrong. Transitive Venus was used to measure the size of solar system. Yes, that's right. That's correct. Interesting why transitive Venus rather than transitive Mercury. The alignment was more rare, and it gave us essentially a longer time frame and allowed us to more accurately determine whether or not our math was correct. The reason transits of Venus were so important to astronomers is because first it gave us an opportunity to predict an event, and then if our prediction was wrong, it helped us to correct our math and improve the quality of our orbital calculations. Astronomers love transits because it's that extremely rare alignment of two things. That's a very precise metric to add to your orbital ephemeris. So yeah, it's a good question. Extrasolar asteroids. Yeah, probably. We were recently visited by one. We named it Oumuamua. You may have heard about that. Or maybe a comet. But yeah, we now know there are interstellar bodies roaming between star systems. They certainly formed within a star system, but then were ejected via one mechanism or another. That's a good question. All right, let me look at the. Let's do. We went over by 5 minutes, but I want to see if I missed any questions. Is it true that we used to have another planet between Saturn and Uranus? Maybe. Let's see. Mr. Channel, donate to maintain the. Oh, thank you. Donations are something we'd like to do. We're hoping to have a new friends group soon, and they could certainly be very helpful to us in the realm of donations. As it stands, you can contact us via our email, and we can talk about that. But yeah, thank you for asking. Is there an app for? I get that question a lot. As far as phone apps to predict the positions of things, there's so many now, and there's different platforms. So I usually just recommend searching for planetarium, the word planetarium in your app store, and then reading people's reviews and looking for the ones with high star ratings. I like the one I use a lot is called Mobile Observatory. It's not technically free, but it's worth the $5. I think I paid $5 for it, and I think it's worth it. Yeah. Ooh, this is a fun one. 30 seconds on Trojan asteroids. I have a nice animation about that. That's not really a tangent either. That's kind of on topic. Hold that thought. So here are the orbits of a lot of asteroids. And what you're seeing here are the main belt asteroids. That's what all these asteroid orbits are. But we've also discovered that there are asteroids ahead of, so to speak, and behind Jupiter in orbital resonance. And I think I have an animation for that. Hold that thought. Yeah. So this animation may not be of the best quality, but it helps you understand. We have two families of asteroids here. The green, and by the way, there are asteroid families, yes, and also families of comets too. So we have the Hildes, which are the pink ones, and then that's a family, and then the green are the Trojan asteroids. As you can see, they seem to lead and follow Jupiter. There are points in a body's orbit of orbital resonance where if a body finds itself within that range, that area, it can actually achieve some stability. As you can see, they're not perfectly in lockstep with the asteroids or Jupiter, but they are there. They are staying somewhat put. And essentially, the Trojans are simply in orbital resonance with Jupiter and other asteroids. And the reason this animation is quite cool, notice that we can clearly see gravitational interaction between the Trojans and the Hildes, and it causes the Hildes to have a sort of triangular orbit. I think that's pretty cool, yeah. So yeah, I don't know if that answers your question a bit, but that's a brief touch on the Trojans. There's lots of other bodies in our solar system besides just the Jupiter Trojans. However, that term Trojan is often applied to bodies in similar orbits, even though it may not be referring specifically to the bodies in this particular animation. Yeah. So because they became popular. Yeah, I did not know about the triangular aspect. Isn't that fun? Yeah. Orbits are not always loop-de-loops, are they? But again, this is why I said this isn't really much of a tangent. This is pretty much on topic. The reason it's possible for them to take on such a weird, in this case, let's call it triangular orbit, is because these are minor bodies. They comprise very little mass, and they're easily perturbed by other bodies. You would never expect a planet, for example, to have such a wild and crazy orbit. For it to do so, it would have to have been perturbed by some other extremely major body. I'm not saying there are no planets in the universe like that, but it would be a much less common occurrence than having asteroids and comets acting this way. Yeah, good question. Well, did we learn anything? Did we learn anything tonight? But Troy, what are we going to talk about next week? Next week, we're actually going to do a little history lesson about Goldendale Observatory. We'll talk a little bit about how eclipses factored into the founding of this facility, and maybe share a few pictures. Recently, a nice fellow, friend of the observatory, sent us a CD full of pictures that he took here when he was a youngster back in the 1970s. So we might share a few of those images. He gave us permission to do that, so that was nice. Yeah, so talk a little bit about history of Goldendale Observatory next week, and the connection to eclipses, and also the Einstein angle, since someone brought up the whole relativity experiment. No, Einstein was not here, but some work was performed on his behalf here, so we'll talk about that. All right. 30 seconds, and then we're done. This is your last chance, my friends. Let me summarize what we went over tonight. There are certain times where it's easy to see Mercury. Most of the time, he's hard to see. I gave you a list. I'm going to fly through it again really quick. So January 24th, which is today. March 6th. May 17th. July 4th. That's an easy one to remember, 4th of July. September 14th. October 25th. Those are all either eastern or western elongation events of the planet Mercury. Those are your best shots of seeing planet Mercury. Remember, if it's at greatest eastern elongation, you'll see it setting in the west after sunset. If it's greatest western elongation, you'll see it rising in the east before sunrise. I know that's opposite. And by the way, for thoroughness sake, Venus will have greatest western elongation on March 20th and greatest eastern on October 29th. So in the case of Venus, only 2 elongation events in a year, whereas in Mercury's case, we had 6. And by the way, all the dates I just gave you pertain to the year 2021, which is this year. Welcome to the new year still. It's still January. I can still say Happy New Year. Yeah, a very Happy New Year to all of you. Yeah. Impressed, brain exploding. Oh no, what have I done? Yeah. Billions and billions. Yeah, that's funny. I would never pretend to be Carl Sagan. Although I will say, whenever someone brings up Carl Sagan, I always feel a need to rant a little bit, or maybe pontificate a little bit about science, the difference between science outreach and science itself. You can be a darn good research scientist and be a terrible communicator. Science communication is very important. I would argue that Carl Sagan's greatest contribution was not his science, and of course he was a scientist, he was an astronomer, he was an astrobiologist, back when that was like a new thing. His greatest contribution to science, in my opinion, is awareness. His famous show Cosmos and his various books increased public awareness of science, because Carl reminded us of something that I'm obsessed with reminding people about. He reminded us that science is not beyond you. Because one of the reasons people they don't bother learning about science is because they think they're not smart enough. It's wrong. I would argue that everything we talked about tonight in this show would not be beyond anybody. Now, if you tried to prove this stuff mathematically, yeah, that would be beyond most people, because some of this requires, genius level mathematics, mathematicians, career mathematicians, or physicists in the modern age using advanced supercomputers. Yeah, so if you want to prove this stuff, yeah, that's hard. But if you want to just learn about it, you don't have to be the world's greatest mathematician. You don't have to be a computer scientist. You don't have to have a supercomputer in your basement. By the way, you own a supercomputer. This thing in your hand that you have in your pocket or whatever, this is more powerful than supercomputers built in the 1980s. Think about that. People could be doing advanced astrophysics on your cell phone. And what do you do with it? Not that. Yeah. Anyway, looking at pictures of cats and whatnot. Yeah. Well, I hope we learned a few things. Next week, talk about Goldendale Observatory. We learned a bit about Mercury in this show. We somehow still managed to go over time, although I'm happy to do it, by the way. I'm not complaining. I just always worry about your attention spans. You guys should always keep looking up. If you enjoyed this video, please like and subscribe. That helps us out, makes the channel bigger and more powerful, gets more people watching. Someone asked about donations. If you don't want to give us money, donate your time to watching these shows, and again, liking and subscribing, and also telling your friends and family about them. Especially if they're teachers. I think some of this material might be useful to school students. I hope so, anyway. With that, I hope we had some fun. I will be in touch, and stay safe, stay curious. Have a good night.